Dear friends, today we will present some measurement systems and sensors that we use in digital systems in order to perform the control of digital systems or hardware in the loop systems. So first of all, we will present some measurement and some sensors. For example, in our environment variables, we will find the temperature, humidity, pressure, force, torque, and acceleration, speed and position, and also altitude, we're using MEMS, etc. For the electrical variables, we will see the current sensors, the voltage, and other magnetic sensors. So there is a lot of new technology here with the output being more digitalized, and they use also MEMS, micro electromechanical system. So we'll review all of this. And the main process here is going from the physical environment using the sensor, and then the signal is conditioned, adapted using analog or digital output. Then it can be transmitted over air or over some protocols, over wires, through this means, and goes to the acquisition system and being acquired by the CPU through analog to digital converters. So we will see all of this. And at the end, we will perform some computation using this, the value from the signal, and we'll use them to control or to store data and analyze it. Okay, so first of all, we will review some temperature sensor. So you have visual sensors that are used by humans, like the bimetallic, the thermometer, change of states. You can have here, for example, for fish tanks, you can observe the value of the temperature of the fish tank using some colors on this kind of sensors, or with non-contact sensors that we found mainly in these last 2 years a lot because of the COVID. We have here infrared sensors, but all of these are used for humans and not for machines. So we need some temperature sensors that can be acquired, that the output can be acquired. So among them, we found the PT100, which is an LTD sensor. We will see it in details. The thermistor, the thermocouple, which is widely used, and new sensors based on integrated circuits. So first of all, the resistance temperature detector. So it's a fine wire of particular pure material, like platinum or nickel or even copper, that is rounded and wrapped around a ceramic or glass core. And this element is put in the environment that we want to sense its temperature, and the variation of the resistance of this wire is linearly proportional to the temperature. So this is the why we choose this kind of pure metal. And the standard platinum resistance temperature can change according to -200 degree to 1000 degree centigrade. And then how we can sense the voltage is that we use a Wheatstone bridge here to sense this resistance using a power supply and three well-known resistance. So the idea is to put some current here. If we have more, we want more performance and less disturbances. We need to inject a constant current through this platinum 100 ohm PT100 resistance, and then we sense with other cables, not the ones that will produce a voltage drop here. So we use other wires like you see here, you have the wires that will conduct the current, the 1 milliampere current, and the other ones that conduct no current and that are linked to a digital voltmeter. So this is very accurate as mean, but it requires this kind of system. The other temperature sensor is called the thermistor. It's mainly used as a system to shut down a process. You have, for example, the NTC, negative temperature coefficient, and the PTC, the positive temperature coefficient. This one, the resistance increases as the temperature rises, and the NTC is the controller. So this is used, for example, to perform fuses and protection. This is also used, for example, in boilers to stop the heater in the boiler. More systems are the thermocouple. So the thermocouple is a junction between two dissimilar electrical conductors, and based on the Seebeck effect, they will produce a voltage, and this voltage depends on the temperature of this hot junction. The problem is that this temperature is this voltage is very low, so we need to amplify it, and we use for this a system here. For example, here I present you the max 31855K, or the max, this is an older one. It's the same one, but the same pin-to-pin chip, but it is older, the 6675. You can find it on AliExpress, or it's very common. The temperature area is very wide, so the range is from minus 200 degrees centigrade to 1350 centigrade. The most common thermocouple is the type key. As you can see here, you have here a type key 1. So this is a one with plastic around it, and this is very fine. As you can see here, two battery AA battery. You can see what is the size of this thermocouple. Of course, you must not touch these two conductors must not touch each other. And here you have the max 6675, and it's a conditioner, so it will compensate, it will measure the local temperature here, it will compensate what is called the cold junction, because we have soldered the thermocouple here on this board, and then it will also perform a thermocouple to digital converter, and it will send this when the microcontroller asks it through an SPI interface, serial peripheral interface, which is digital. So you have no noise, no disturbances. So we did some experiment with this using Bluetooth here, rotating these things around machines to measure them. I can show you how we connect this to the microcontroller. So this is the T plus and T minus cold junction. This is the hot junction of the thermocouple, and you connect them using the SPI, master input, slave output, a serial clock, and a chip select. So the microcontroller will ask, using a chip select to 0, and using a clock, will ask this transducer to send him the available data. So as soon as he performs this, it will answer with the data. As you can see here, you have the clock, and you have the answer on the MISO, slave output master input. And as you can see here, this information is then used to be stored and be acquired by the microcontroller. Nowadays you have other integrated circuit sensors like the Dallas DS18B20, which is very known, but it's not very accurate. And less expensive ones is DHT11 or DHT21. In the Arduino community, you found a lot of application using this. The SHT11 is older, but it's a Swiss-made company called Sensorion who make it. Here you have an application that I produced. You can visit my website with a microcontroller, DSP33F, and the sensor, which is here, which is connected through a particular protocol, which is a two-way one-wire protocol with the serial clock, and the information is stored on a micro SD card. This is the DHT11 within WEMOS, ESP8266 microcontroller, and other stuff like an inertia measurement unit and an OLED screen. So you can find some information on this. Other sensors that we can find in these hardware-in-the-loop systems are strain gauges. Strain gauges are devices that experience a change in resistance when they are stretched or strained. So you can, with this small displacement, which are in terms on micrometer, we can sense how something is stretched, and with this you can sense, for example, a change in weight. You find them in the kitchen weighting system, you find them on human weight system, and as always you must have a whetstone bridge, op-amp amplifier, etc. Differential amplifier. Same system as you have a displacement, but in this case you have a very thin diaphragm. Here you have some gas between these two, and it can sense the pressure differential between P1 and P2. Okay, so this is a little bit exaggerated, but you can see because this displacement of this diaphragm will change the current into these coils. Okay, so the inductance seen being between L1 and L2 will differ. In first, the L1 is equal to L2, and if the displacement is positive in this way, so you have this change. Of course, in this you have, in the bridge, you must have AC voltage. So this is inductance. You have the same with using capacitance change between these two things. Okay. Now we go through distance measurement. There are ultrasonic sensors. This one is very common in the Arduino community. It costs about 5 euros, less than 5 euros, and then you there is a chip here that will, when you trigger it, it will start transmitting a 40 kilohertz pulse here, and this will reflect on. So it is transmitted, it is reflected on an obstacle, and it comes back. And then by measuring the time spent between these echo, so this signal is proportional to the measured distance. So with the small calculation, you can sense the distance, but it's not very accurate. Then you have a more recent one, which is called time of flight. So time of flight, the more known is from ST Microelectronics. It's the VL53L0X. Here you have a demonstration that I made using an ESP32 with its I2C connection. So you have only 4 contacts to connect, which is the voltage, the ground, and the serial and data connection with I2C to this microcontroller. The library are available, and in less than 10 minutes you have your sensor working. It measures up to 2 meters or 2.2 meters, It's very accurate, it's very small, as you can see here on the breadboard. And I leave you see here this information on this data. It's about €2 on AliExpress. Okay, now we go with the other MEMS sensor, like the accelerometer and the gyroscope. In early they were separated, but now you find them in EUMU, Inertia Measurement Unit, IMU. You find them, this EMU, like the MPU 6050, this one, this chip. As you can see here, you have X, Y, and Z mounted with also barometric sensor. This is 9 degree of freedom. That means that it measures the gyroscope over the 3 axes. So it measures also the acceleration over the 3 axes and the magnetic direction. So it's a compass, 3D compass. So it's 9 degree of freedom. You found them in quadrotors, on segways, and systems that must measure the attitude of the embedded application. And then the transmission can be done using NRF, like it's the example when we measure the acceleration in tangential and in normal acceleration on a rotating shaft, and it is transmitted through this NRF to the D-space board. Here is a closer look on the transmitter and 2 accelerometer. You see the size of 2 AA battery. So all these projects are made by me. This one is using a Bluetooth, a Wemos, and we don't see the accelerometer, but the MU is on the back side of this board, and a LiPo battery with its charger. And you can fix this on a leg to see if a patient is sleeping or it is walking, and you can sense it through a database, MySQL database or fibers. Okay, let's now move to the electrical world, and for the machines and motors, what we need to control a motor, what we need in this kind of system as generators or motors. We need encoders to know the position or the speed of the motor. We need current measurement. So for 3-phase motor, we need almost 2 measurement only. In some application, we need also voltage measurement to synchronize with the grid if you want to implement a generator, double-fed induction generator. We need some PWM interface board to control the inverter that will feed the induction machine or the synchronous machine, and its power is taken from a rectifier from the power grid. So all this is controlled through a DSP board or digital signal controller. We will choose in this presentation the DS1104 from DSpace, and you see it in more details. So this is an image of the motor of the DSpace control board. This is only the CPLD, it's the extension or the connection board, and the board is inside the computer. This is a load, or it can be if this so this is a motor, so this is a DC motor for the load. Okay, so the current measurement is like this. You have 2 LM sensors. We see them in more details. We have the voltage sensors. So we need to put them on a circuit board. Another kind of system is this induction motor, 5.5 kilowatts with its encoder. And on the rotor shaft, you will find another motor or generator and another brake. You can see here the inverters, these 2 inverters that will control the special machine, and also the conditioning of the measurement, which is filters. Let's start with the encoder. So the encoder is a technology that is an optical technology when you have some electronics that will produce some light using LEDs, and this light will go through some holes and it will produce some signals. So if the light which will go through a hole, it will produce a 1, and if it is not through the hole, it will produce a 0. And you have two sets of lines here, which are displaced by 90 degrees, and you can see signal on channel A and channel B, and you have also synchronization channel, which is called also the index. So we have many names. You have A, B, I, like index. You have 0 and 90 degrees and the index. And depending of the number of holes through a tool, it can give you more resolution. So the more holes you have on 360 degrees, the more accurate will be your position. The problem is that this measures only the incremental position, so by how angle it moves, and not the absolute position. You can have the absolute position once when the disc goes through the index hole. Okay, so you have to make a turn to see and to synchronize your position, your absolute position measurement. Otherwise, you only measure the incremental position. So in order to get the absolute position, we can have another kind of encoders called absolute encoders. So here you have not only the incremental ones, okay, you have for each LED you have a circuit. Here we present 1, 2, 3, 4, so 8 LEDs, so it's an 8-bit absolute encoder, and you have these 8 paths, as you can see, 1, 2, 3, 4, 5, 6, 7, 8. So you see the inner one, it's 2 bits, it's 0 and 1. So 0 and 1. But the outer one you have 0, 1, 0, 1. And then you have 8 possibilities, and you have 16 possibilities, etc., etc., up to 2 power 8. So the phototransistor will capture the light, and it will produce a binary signature of the position. The problem also arises when there are a lot of changes. For example, here you can see a lot of changes, here you can see a lot of changes, and you can have some mismatch if the change occurs on one and not on the other. And this can give you a false position. So a binary coding is not very not commonly used, and we prefer a gray coding, like for example this gray code of 12 bits. As you can see, gray code is different from binary code when you have only one that will change at a time, and not like this when you can have many that will change at a time. You can type gray code to have more details about that. So this incremental encoders, these absolute encoders are very expensive comparing to the incremental encoders. So if you want to sense these positions, absolute position, we use also resolvers like this one. This is very, very small. It's like 2 or 3 centimeters here. You have a coil here, that in inner coil that is excited with let's say between 10,000 and 14,000 or 16,000 kilohertz. And then you have fixed coils in alpha and beta, which cause sine and cosine S1 and S2 coils, that gives this low changing signals. I present you here the ones that are in a Nissan Tino hybrid car. So you see here the sine and cosine. You see a 90 degrees shift, and you see a very high frequency here of the signal. So the envelope is the sine and cosine, and you have here the 40 kilohertz signal. By the way, this is a test car, that Nissan developed in the earlys of the 2000, and with two electrical machines and an ICE with clutch and CVT, but now it's no more sold. And we have experienced some result with the current on when we drive it with the at 5 kilometers per hour, with the voltage of the inverter being applied to the motor and the current taken from the motor. So they use this resolver to synchronize the control with the position of the motor. Here is an example of how you can choose an incremental encoder. So you first choose the type of shaft, the diameter of the shaft, and more important, the resolution. It's better to choose a power of 2, like here 1024 points. So it's around per round you have how many changes by turn. And then you can have different kind of incremental encoder. You can have only A, so only one path, A and B, so what I showed you, the A and B and Z, which is the index, and also the complementary signal. If you use the signal, it's complementary, it can give you a better noise rejection. And then you have also, you can choose the output circuit if it is an open collector or things like that. And then you connect this through on your board. Here in this example for the CLP 1104 of D-Space, you have two connectors for the incremental encoder interface. So you can find the power, the board, DSP board can power it by itself using 5 volt internal power, and it can sense the Phi0 and Phi0 bar, which is the complementary, and Phi90 and Phi90 bar, which is the complementary, also for the index, and you have the ground. So here you have the best connection because you have the immunity to noise using the signal and its complementary.